So here we are in the lab again, and we have our front end parts on. So now we have to check them. And in order to do that, we're going to use Microchip's development platform called MPLab X. We're going to use that to write a little code, just a little bit, and toggle those address lines coming out of the I/O connector. And so we'll get into the heavy duty details of everything later, but I'm just going to do the minimum to get in there so we can get our circuit qualified and move on to the microcontroller. And then that's when we're going to really get into the hardware and the code. And so let's get to it. Okay, so we're at a point now where we have to have our software to create the code for our board and for that I use for MainBrain. So that's called MPLab. It's a microchip IDE, an integrated development environment. Actually, it's called MPLab X now. That's the newest one. So it's what we want to do. We got to get that. So it's free. So we just go to microchip.com and go to Tools and Develop and MPLab X IDE and just hit the download. It'll bring this up. So you got Windows, Linux, or Mac options, whichever you use. And just hit download, and then you download it to whichever directory that you want. And then you install it, and it'll take, if you install everything, which you probably want to, really, it'll take like 5 minutes. So be prepared for that. But yeah, download it and install it, and then you're ready to create a project and write some code. But we'll get into that in more detail. But right now, we're just going to write a little code and check out our address lines, our address select lines on our I/O card, and make sure the circuit works okay. And then we'll go from there. Okay, now that we've downloaded the Microchip IDE, then we need a programmer so that we can get our firmware, our program, into our microcontroller. And so to do this, we need one of these devices, these programmers. And so the cheapest one is the Snap. The Snap's like 35 bucks, and it works great. It doesn't have some of the advanced features for like in-circuit debugging and stuff like that. And I get by just fine without in-circuit debugging. I haven't had to use that yet. There's a lot of ways you can debug and troubleshoot before you have to resort to that. Some people just like it and use it automatically, but you can or you can't. That's up to you. So then the next one is the PIC Kit 3. It is a little bit older, but it works as good as all the other ones. It might not support some of the newer processors, but you can always update the firmware. They have firmware updates, so I don't know how long they will support the PIC Kit 3. It's been around quite a while. Then they have the PIC Kit 4, and that's programs faster and supports more processors than the PIC Kit 3, although I haven't ran across a processor that the PIC Kit 3 doesn't support. but I haven't messed with all the processors that Microchip has. And then there's the PIC Kit 5, and it's a lot like the 4. I don't know a whole lot of difference about it, really, other than the connectors. Now, these plug in to your USB on your PC, and you got this ribbon cable here, 6-pin ribbon cable, and that's so you use the ribbon cable to connect to the PIC kit to your microcontroller. So they plug in. Usually the red one is pin 1, and so you just stick that in there like that. And then this part, this end right here, goes to your board on the ICSP connector. Okay, so basically this purple one on the end isn't used anymore. They might use it for like in-circuit debugging or JTAG stuff, but I'm not sure on that. So then the other end plugs into the USB on your PC. So there's PIC Kit 5 has the type C, the USB type C like the Samsungs use. And I just happen to have one here. We'll plug it in and see they have an LED there. And that's all you have to do. Once you download the IDE, all you have to do is just plug this thing in and it's ready to go. It'll, depending on your processor, it'll download its own little program when you set up your software. So then the PIC Kit 4 uses the micro, the USB micro, like the old Samsungs. And then the PIC Kit 3 uses the USB Mini, the same one Mainbrain uses, because this is actually a pretty robust thing. But everybody goes to the Type C or the micro. And then the Snap uses the micro as well. Okay, so that's options to program. This is the cheapest, and this is probably the best. But they all work good enough for us. So there's no reason you can't spend 35 bucks on this and do everything that we're doing here in the lab. You just don't get a fancy case. Okay, so that's how we get the program into our board. Okay, so we're at this point, I'm assuming that you have downloaded MPLab and installed it. And just to make things simpler, it takes longer, but just install everything. And then that way you don't have to worry about details and choices and decisions. And then later on, you can change it and stuff. But I mean, there's nothing wrong with downloading or installing the whole thing. All right, so I'm going to load it up here. And we're going to go into it in more detail. Once we get the microcontroller on our card, then we'll go into more specific detail. But I'm just giving you a taste right now so you can see what it takes and just getting an idea. All right, so here's our code. There's 3 different sections. Well, actually 4. That's the output here of your compiler and stuff. And this is the code section. This is where your projects are kept and managed. And then this is information about how much memory you've used and stuff like that. So this is Mainbrain's code right here. So we're going to have to initialize our IO board. So to do that, we're going to create a file, and it has a function, and then we're going to call that function from the main program, and that will will configure our address select lines on our IO card. and that's what we want to test right now. So basically, give you a quick rundown. For main brain, I have a header file, and that's where you declare your global variables and your functions. And then you have your source files, and I have a source file for all the different modules and some utilities and some operating system stuff for main brain. So when you compile it, it compiles all these together into one output file. So we're going to create a new file for in here, and we're going to call it IO board. So we're going to take this file here. This is the Flash initialization and functions, has Flash functions in it. So we're going to use it as a template so we don't have to type everything in. So we'll just go File. Oops, didn't want to do that. So we go File and Save As. And then we'll call it IO board. .c and save it. And that doesn't change the Flash file. It just creates a new copy of it. So then we got to change it. This will be IO board.c, and it's 2025 now. Everything else applies. We're not going to worry about that. And so we don't need that. And then we'll just code for the IO board. All right. Let's get that over a little bit like that. All right. And that's all we need. And then everything here. So we don't want these variables in there. And we don't want the code for the Flash or any of the functions for the Flash. And then we're going to rename this function to IO board init for initialization. All right, so that's all we need right here. So we need to copy this function because we have to declare it in mainbrain.h. So we come over here to mainbrain.h, and this is for our IO board. So we don't. I've put that in already. Okay, so that's already in there. And so we can come back over here. So that's in there. And so now we have to add our file into our list to compile. So we'll add existing item and ioboard.c. So that comes up here. So now we're ready. We'll do a compile, a build, and see if it works, see if we have any errors. All right, so it likes that. And so now we can add our initialization code here. But we have to call this function from the main program. So we haven't done that yet. So we'll grab that name. I like to copy. I'm not a typer. I'm a copier. So I'm going to put it in here. The speaker beeps when everything is initialized, and our IO card will fit right in here. So we're going to do a comment for initialize IO board. Okay. And then we'll paste in our function name here. That's a function, so we have that. End it with a semicolon. Now, the way I have it set up, I write a value to the LED port to indicate that we are going to initialize something, so that if it hangs, when you call that initialization code, and if it hangs, then you won't get to the next value. It'll display this, and you know, since hexadecimal C is displayed on the LED port, you know that this was called. but it didn't complete because it didn't initialize the next thing. So then we have to write a value. So indicates the IO board is completed. All right. Oops. All right. That's our comment. And then we'll just copy this here. And then we'll change that value. After C comes D. That's hexadecimal. And then if it hangs here somehow, then we know that this was the last thing that was initialized. If it hangs here, we'll see this. So we know that this initialized okay, hit here, but this hung. All right, that's just a little power on self-test thing, that kind of indicator. So that's where we're going to call our code here on our file. So everything in here we put in here will run when it goes through our boot up and it comes to the board initialization here. It calls this function over here and runs our code in here. So then, now the hard part. So we got 3 address lines and we have a 74 AC 138 chip. So then we want to set up our board so that we can control the address that goes to that 138 chip. So probably the first thing we should do is to load the data sheet for the 138 chip. So I have that in my files here under my project and under IO board and data sheets. So we have the 138 right here. Get rid of that. We don't need that. Get it up here where we can see it. All right, so this is our chip. This is the logic diagram of how it works. And for every chip on the board, we have a data sheet because it tells you how it works and what you need to do to make it work and all that good stuff. Let's go back to here. So basically, main brain, well, on the IO card, we have this all set to be enabled. So we don't have to worry about that yet. I don't know if we'll do anything with that later or not. But then, so we have our 3 address lines. So it's a binary value, 0 through 7. So you have 8 possible 8 possible numbers. So that selects which output goes low. So normally these outputs are high. So as long as these are selected, then all of these outputs are high except for the one that's selected by these addresses. So if these are all 0, this output Y0 goes low and the rest of them are high. And then if you put a 1, if you bring this one high so that it's a 1, that will select 1, and then 2 selects 2, and then all the way up till 111, which is 7, selects this one. All right. So that's how this chip works. So we're going to use MPLAB to change the value here and make sure we have the right value out. So I'm not too worried about the chip, but we need to check to see if we can get the right value here from main brain. Okay. So then we will look at the pins here. And so you can see, this is our package here. We got VCC on this side and all the outputs are here, except Y7 is over here. So we'll just have to remember that when we get that far. But all the outputs, all this side of the chip are outputs in sequence, 0 through 6. So we know that now. So then, all right, so we'll go over to our IO card schematic in Fusion and zoom in here. So this is our chip. So we got these 3 address lines. See, these are set up right now, just hardwired to enable the chip all the time. We may need to change that, but right now we're just going to deal with these 3 lines right here. So it's what we need to do. We need to change the value on these lines and count through the sequence to turn on these 0, 1, 2, 3 all the way to 7. So, and then once we do that, we'll check our output here and make sure it enables these chips here. And then we're done with that until we get the microcontrollers on there and set up. So I'm using these lines here off of the connector coming directly from mainbrain. So it was originally intended to be an optional serial communication port. And so I think I'm gonna, at least in this case, they're gonna get changed to A0, A1, and A2. But for the IO peripheral cards that we add on. So this is going to be the front end for all the cards connected to mainbrain once I have the bugs worked out of it. So that's basically what we're doing at the same time we're doing our IO board. So we're going to have to figure out what pins on mainbrain, what pins these are on mainbrain. So we look at this connector and we know that it's the 3 pins by underneath BDD. So we have these names, and I'm going to probably change the names on this. And that's kind of a process too, and we'll have to get into that. All right, so we go over here. Let's see. So we want to load up mainbrain. Where's mainbrain? Right here. And we want to load up the mainbrain schematic, okay? Because we need to know what port pins we're going to have to use. All right. So there's our mainbrain schematic. So then this is the IO port. And we know that it's these 3 pins right here. So let's get our eyeball on it here. And we'll start with the first one, which should be our A0. So then this is port pin RD15. So it's port D bit 15. All right, so then we come back over here. So we know that it's D15, and we know that it's address 0. All right, make it 0. And so we know that it is port, let's do a comment, port D, pin 15, or bit 15. All right, so then we have to initialize that pin as an input or an output. So it's going to be an output. So in microchip language, and we'll get into that too in more detail. So don't feel like you don't know what's going on, because you probably don't at this point. But this is just to give you an example of what it takes. So this is port D, so it's tris D, which I believe it's like a tri-state command thing for the port. And then you just put bits, because we're going to just do one bit, and then dot, and we'll select it. We know it's D15. So it's a 0 for output and a 1 for input. So we want output, so we put a 0 and a semicolon. And that initializes that port pin as a output. Okay. So then, whoops. So then the next thing, we want to put a value on the pin to start. So we're going to just start it with a 0. So it's going to be port D bits, and it will pop up with which one you want, and that's already 15. So we want to start it as a 0, a low value. All right. So let's put these two together and make it a little neater. And then, so we're going to do the same thing for A1. And then we'll come down and do the same thing for A2. All right. So now for A1, we got to figure out what port pin that is. So we come back over to our schematic for main brain. And so we know we have our eyeball on. So we'll hit that right there. And that we know is our A1. And that's port F, bit 13. So F13. So we come back over here to our code, and we can just copy these things. I'm a copier. All right, so F13. So we know that it's port F, so we got to change that. And F. And then tris F13. Okay. And you can just test it by just hitting the point. It'll pop up in F13. And so we want that to be 0, 2, and an output. Same thing. All right. So let's take out that space. Get in another space here. And we'll just copy this ahead of time since we're here. All right. So then we got to figure out what port pin this one is, A2. So we go back over here, back to our connector, and use our eyeball to look to see where it goes. And it goes to RD14. So we come back to our code, and that's port D. Port D. See, I could have copied this and saved me a little bit of time. D14. And I'll just make sure. With a dot and D14. Okay. And that's also going to be an output, and to start with, all of them are going to be 0. All right. So that's our initialization code for the 3 port pins. Okay. So then we will just build it real fast to see if everything is good and it likes that. We didn't find any errors. So now we got to send it to main brain. So that's when we click here, send it to main brain, which is a make and program command. So it finds main brain's microcontroller, and then it programs it. All right, so now our code, it reprogrammed the whole thing. Every time you change something and you want to update it, you have to send it to main brain. It sends the whole program. Okay. So now we should have 0 for our address at our 138 chip. So these ones, A012, should all be 0, and this output here should be 0, and the rest should be high. So now we have to take a look at the scope and see. You could use a meter too, but we're gonna run a sequence of these, and you can look at how the output changes. All right. But so we'll fire up the scope. Okay, so here we are. um, I thought this would be a good time while we're getting set up to show you plugging in the PIC kit to MainBrain. So we're gonna first we'll plug in the USB that's connected to the PC. All right, and then we got our little I/O connector here, and we'll plug that in so that the red wire goes to pin 1, and then we'll tip MainBrain up here where you can see it, and we put the red wire always goes next to the jumper. And in fact, I put the jumper close enough to the ICSP connector that you can't plug it in the opposite way, but you can turn it around backwards. All right, so we got that plugged in just like that. And then we will plug in MainBrain's power. And see, you hear that beep. That is that indicator we've seen in the code that everything initialized without hanging. Okay, so let's get our scope probe over here hooked up. So we want to put our ground right here on there, like that. And then we can probe it. So from our code, we know that everything should be 0. So these 3 pins coming out of so this is VCC. So we see VCC there. So we should have VCC right here. And we do 3.32 volts according to the scope. Then the next one should be low. The next one should be low. And the next one should be low. Okay? And that's all good. Okay? Okay, so back to our schematic. So we have zeros on each one of our address lines. So now next, we're going to have to check to see if the output here is 0. Okay? So we're going to check out which pin on our jumper is 1. And we know that this one side here is our outputs. Okay? So we'll go over to our PCB here, and we will zoom in here. So we know that it starts at 0 from our data sheet. This is our chip right here. So this is BDD. Then this is 0, 1, 2, 3, 4, 5, 6. And if you remember, 7 is right over here, which is here. So it goes down in sequence. So these across here, 0, 1, 2, 3, 4, 5, 6, and 7. So now that we know that, we can check these. All right. Okay, so now we want to verify that since if we have 3 zeros, which we checked before, that we have a low on 0, output 0, and the rest are high. So if we check this pin right here, it is low. We check this pin right here, it is high, and just go down the line. Whoops. high, 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 and high. Okay? That would be a win. So then we will check the next one. So we'll put a 1 on A0. Okay? Now, let's see what our pins are coming out of the connector. So A0 is high. That's what we want. A1 is low. And A2 is low. So we pretty much proven A0 is good to go. So then that is, that's an address 1. So this is address 0 right here, which should be high. And output 1 here should be low. And then the next one should be high. All right, and we're pretty sure the rest of them are high. You can check a random one to make sure. But I mean, the chip's working, so if we're putting the right signals in, we should get the right signals out. So we're good. We're really good. So now we go back to the code and put a 0 back on A0 and then as a 1 on A1, which will be a binary 2, which will bring us down to the next pin being low. All right, so we want to take A0 and put it back to a 0, and we want to change A1 and make it a 1. Okay, and then we'll send it to main brain. Okay, and then we will go back to the scope and check it out. Okay, so then we just want to verify at the connector that we have the right address going to it. So we have A0 is low, A1 is high, and A2 is 0. All right, so then that is an address of 2 binary. So then that should be pin 3 or output 2. So 0, 1, 2. So we should have a high, and a low. And we do. And the next one should be high. Okay, very good. Next. Okay, so now we're going to change this one back to 0. So we're done with A0 and we've qualified A1. So we just have A2 left. So all we have to do is put a 1 in here like this. Send it to main brain. And go verify it. Okay, back to our connector. So AO is 0. A1 is low. And A2 is high, just like we wanted. So that means that is an address of 4. Okay, so that means our output 4 is going to be low. So let's check our outputs. So output 0 is high, output 1 is high, output 2 is high, output 3 is high, and output 4 is low, and the next one, output 5, is high. All right, so there we go. We have qualified our addresses. All right, so now let's go to our code, set the address at 0, and we'll put a shunt on here on our jumpers, and we'll just check to see if the output goes to the right pin on the chips, and we'll be done. So we'll set A2 to 0, and that's address 0. Send it to mainbrain. All right. All right, so let's put a jumper on output 0 right there. And we'll check and follow the signal. So let's look at our schematic real fast. So we got a jumper, a shunt across here. So that's connecting these outputs to output 0. So let's get our eyeball on here, and we'll hit that. So it comes over here to the microcontroller to generate an interrupt. We won't worry about that since the microcontroller ain't on. So the next one is our AC 245, which is on the bottom side of the board. So it's 20 pins total. So pin 19 is the output enable for this chip. So we should be able to verify that. And both output enables 1 and 19 on the 244s. So we'll do the 244s first since they're on the top of the board. Then we'll flip it over, check this one, done deal. Okay, so we should be able to check our signals for the output, which will enable the buffers. So we should have address 0, which is output 0, should be low, which it is. And other ones are high. Okay. All right, low on output 0. Okay. So now we'll put a shunt across there. And so that should read 0. Uh-oh. That should read 0. So something's holding this line high. Let's see. 0 on output. 0 is 0. So then we go to this back part that connects it. So there's something wrong. Something is holding this line high because the chip shouldn't pull it high. It should be low or floating, high impedance. All right, so let's go to our PCB and look at the traces and see what we did. All right, so let's put our eyeballs on. All right, zoom in. So it's this guy right here that's giving us the problem. So what do we see on here that would cause us to bring something high? So I don't really see anything. So I think it's time to do some troubleshooting, and that's why we're here. Okay, well, that was a surprise. I was expecting to wrap this thing up like right now. So there's nothing obviously wrong. It has to be something like pins mixed up or something like by putting the 245 on the bottom, somehow it got mirrored wrong or something. So there's an output driving that somewhere. It's not shorted to VCC, so it's got to be an output of the chip. So either I blew a chip by sticking the probe on there and crossed some pins, or we have a serious layout problem or something. Maybe the pin, maybe the chip, one chip's on backwards, even though the markings on the PCB show that it's not. So I think we'll cut the video here and we'll dive into the troubleshooting in the next video. I hate to leave you in suspense, but I think it's going to be a little bit, it's not going to be just a simple wham bam fix. We're going to have to figure out what's going on. I mean, and that's why we're here. That's just part of the lab. I mean, if it was so easy, everybody'd be doing it, right? So yeah, we're going to do some troubleshooting. It's going to be interesting. I'm kind of interested in seeing what happened, because that should have been kind of wrapped up in the bag. So I'll see you in the next video.